Hi guys, and welcome to Completely Electrical STEM Show. This video is all about how fluorescent lights work, how you calculate all of their parameters, and also their power factor correction capacitor. Enjoy.
So here's the circuit diagram for a fluorescent light. I'm going to be using what's known as the preheat method because the only ballast I've got is an old magnetic ballast. Nowadays you can get electronic ones that pretty much do everything for you, corrects the power factor. They're glorious things actually. And the tube goes there. This is the starter switch, which is essentially a bimetallic strip. And the way they work is two pieces of different metal sandwiched together, and when they heat up they expand at different rates, so one of them will expand faster than the other one and move the contact out of position, so it's like an automatic switch. This here is representing a ballast, which is one of these, just a coil of wire actually. The wire goes in there, coils around and comes out. That is literally all it is. And what they do is they store kinetic energy in the form of current and magnetic fields. This is how these lights work. Your supply voltage is down here. Now what you need is current through here, but 230 volts isn't big enough to jump from there to there. So that's not enough, which is why we need this ballast. So it starts off by charging up the ballast. The current runs through these tiny filaments at each end, which heats up all the mercury inside and just gets everything going. It needs that extra little boost. The circuit then continues round through the bimetallic switch, which starts to heat up these contacts because we have got a current flowing through here. It's not a great deal, but it will be a little bit, and it's certainly enough to heat up a bimetallic strip. When you turn these on, you do get a surge in current, so there's going to be more current flowing through here at the start than when the light's actually running. So anyway, it flows around there for a bit, heating up this bimetallic switch, heating up all of the gases inside here, and also charging up this ballast. Then when this switch disconnects because it's curved around, the circuit's been broken. So you'd expect everything to stop, but the energy in this ballast wants to go somewhere, and the only place it can go is across there, and by that point you'll have enough charge to strike across. Then the light starts its little journey across, starts to glow. Happy days. So that's a very basic explanation of how a fluorescent light works. Once this is established, you've got like a negative resistance, and what it would do is just pull as much current as possible from our national grid. So we need a way of controlling it, and that's the second function of this ballast, because it's creating a reactance, which is like an opposition of current in the opposite direction to any current flow. So it actually slows everything down and regulates the current, which is really handy. But what do we know about this ballast? Not a great deal really. Let me get close there. So we can see this little symbol there. We've got EEI-B2. I've got a lambda of 0.48, and it also says 58 watts there somewhere. There. And it tells me it's a G13 cap, which means that the connections on this here are 13 millimeters apart. That's all it means. So we've got that EEI V2, and you can look these up, but what it means is the maximum power consumption of this is claimed to be 9 watts. The tube is 55 watts. There's probably going to be some more consumption, you know, from the switch and just the circuit itself, but for an approximation, we can say that our light is going to need about 64 watts. I said it had a lambda value on there. Lambda of 0.48, and that's describing its power factor. There is something called ballast factor as well, but I'm not going to go into that on this one. The power factor is important because this inductor is going to pull the voltage and current out of phase by 90 degrees. If it was a pure inductor, it's not going to be quite that for this one. So if that was my voltage, then the current would be delayed. And it's because as current goes through here, the coils of wire are actually going to, you know, the magnetic field that's created are going to cut the coils and generate a bit of current in the opposite direction. That's what we call reactance. Now when this is out of phase, you know, this would represent the amount of true power in the circuit, which is not as much as if they were in sync. So if they were more like that, then we got a lot more power for the same current. So we'd want to correct that. And the way we correct it is with a capacitor, because a capacitor works in the complete opposite way of an inductor. So we're going to need some kind of capacitor in there. Now it will work without the capacitor, but you know, I'm pulling more current out of the national grid than I need, really. And it's just a bit irresponsible in the sense that I'm just creating heat and stress on our system for no good reason, really. So the first thing I'm going to do is work out what capacitor I would ideally like. Now, all I've got to go by is this and a power factor of 0.48. So that immediately says to me that I'm going to need my power triangles. I'm going to need power equation, which for most electricians, they kind of know it as a triangle, and Ohm's law triangle, which looks like this. Now, if you've not looked at power triangles before, then tough, because I'm not going into them now. I'll do another video on them another time, but the places, the labels, if you like, are these. They're all types of power, but it's just describing different parts of the circuit. So this is the reactive power created by the inductor. And I said a true inductor works 90 degrees out of phase from any kind of resistive power, and that's why we end up with this right angled triangle. It's supposed to be a right angled triangle. It's badly done. So that's why we can use right angled triangles to solve them. The power factor is the relationship between the true power and what we call apparent power. The apparent power is just almost like the total, and it is exactly what you might think. It's volts times amps. So if I was, you know, when I had that circuit a minute ago, if I was measuring the current here and the voltage, you know, across there, that's the parameters I'd get, and then I multiply them together to give me a total kind of power, which is, you know, just volts times amps equals power, isn't it? Reactive power is, in this case, because it's an inductor, it'll be reactive current times the voltage, and that will give me my VAR. So I'll explain that in a bit more detail in a minute, I think. So here we are, we've got the power factor, which is a relation, a ratio, if you like, between true power and apparent power. So that gives us an equation, watts divided by VA. So where am I going with this? Well, what I need is to know the reactive power created by my inductor or ballast. And then if I can find a capacitor that creates the same amount of reactive power, that'll cancel each other out. And we're back to an efficient circuit again. So my first target is to calculate VAR. I've got this angle, I've got that. So, you know, this is actually trigonometry, isn't it? It's the cosine of the angle is equal to the adjacent over hypotenuse. It's just been relabeled. So if I transpose this for VA, then I've got that part, and then I can use Pythagoras' theory to work out this amount of power there. So if you don't know transposition, then watch my other videos, because that's shameless promotion there. VA, but here's what it is. It's watts divided by the power factor will give us the VA. So in our case, we said it's about 64 watts divided by a power factor of 4.8. I'm not sure that's accurate. I think it's probably, in reality, probably going to be more like 0.39, and you know, it's going to be a bit less than that. It's quite optimistic. So what we end up with, we've got 64 divided by 0.48. So we've got a VA of 133.3 reoccurring. So let's put that in there. Now, VAR, I said we're going to use Pythagoras, and we are. So I'll just put in that 64 watts there. So Pythagoras' theory says, you know, this square plus that square equals that square. So if I want that square, then it's going to be that one minus that one will give me that one. So again, watch the other video. Done one on Pythagoras especially. Should be uploaded by now. Anyway, to get VAR, it's going to be the square root of my VA squared minus my watts squared. Let's just plug that in and see what I get. So my VAR, square root of 133.3 recurrent squared minus my 64 squared gives me a reactive power of 116.97. Okay, that's good. So this is how much reactive power I would need my capacitor to create. But we're not done yet. Some capacitors are rated in VAR, but the ones that I've got here aren't. They're rated in farads, you know, like the majority of capacitors actually. So it's not that helpful yet, but we're not done yet. Let me just put that value in our triangle. So 116.97. Let's just take a look at these here. Each side of this triangle uses these two equations, but they just have different labels. Now, I'm interested in this at the moment, and what I really want is to calculate the inductive reactance. Here's the two triangles for this side. So if I relabel them, I end up with this. So my VAR at the top, where power would go, because it is a type of power. Voltage will be the supply voltage in this case, to give an approximation, and my reactive current. Then on the Ohm's law triangle, voltage is just voltage again, my reactive current and what we call inductive reactance. So this is the opposition of current, where resistance went before. So this is what I'm after, and the reason why I want that is because there's an equation I can use to find out the actual capacitor size in farads. And the equation is this: to work out capacitive reactance, 1 over 2 pi times the frequency, which would be 50 Hertz for us, times the capacitance in farads. This is telling me inductive reactance. Now, if I make XL equals XC and then transpose for C, it should tell me the capacitor that I need. So this is my target, this is what I've got. So you can see this is common, that's common, there, there. So if I do VAR divided by voltage, I'll get my reactive current. Then if I take the information over to this triangle and do my voltage divided by reactive current, I'll get my XL. So let's do that first. So we got 116.97 divided by our supply voltage, and I'm using 230 volts, which is, you know, our kind of nominated voltage in the UK, and it's because all of this would have been calculated to that voltage, so I'm trying to kind of stick to the manufacturer's stuff here. So I've got a reactive current of 0.51. If I take that information over here now and create a new triangle, if you like, I've got my supply voltage, 230 volts, divided by my reactive current, which is 0.51, I'll get my inductive reactance. So let's calculate that. 230 divided by 0.51 gives us an inductive reactance of 450.98 ohms. Okay, so what I said was what we're after is to kind of say XL equals XC, because if that's true, then we're back to unity and everything's kind of in sync with each other again. So this is the equation for XC. That's supposed to be a C. So if I replace XC with XL, I'll put the actual value in. That's probably easier, isn't it? Now I've got kind of everything known except for C. So now I can transpose for C and calculate the size of capacitor I would need to get it back to unity. So that's 98, Craig, 98. Okay, now to transpose this, I'm going to get everything downstairs, upstairs first. So I'm going to cancel everything down here on this side, copy it that side, and then I can clean it up the original side. So everything's being divided, so you need to do the opposite function by itself to cancel it. So I'm going to be timesing everything by 2 pi FC. I've unbalanced the equation, so I'm going to copy it that side. I really do recommend the other videos, by the way, and don't forget to like and subscribe and click the little bell thing. I'm still not sure what the bell does, but it's good apparently. So I'm going to copy it this side, 2 pi times frequency times capacitor times our XL value, which is also XC in this situation, and then I can cancel this out because 2 pi FC divided by 2 pi FC is 1, and we're left with 1 is equal to that lot. But we're not done yet, we need to isolate C. Now everything's being multiplied together, so I can divide it all in one go. Then copy it this side and cancel that side. So I'm going to do that. 2 pi times the frequency times 450.98. I've unbalanced it. I need to copy it this side. 2 pi times F frequency times our XC, which is also our XL, 98. Then I can tidy up this side. And what we end up with is that the size of the capacitor is equal to 1 divided by 2 times pi times the frequency times 450.98. And anyone who's eagle-eyed there will notice that basically, you know, XC or XL, you know, XC is XL in this case, they've just swapped places. So you could save yourself all that and just, you know, C equals 1 over 2 pi F XC, or XL in this case. It's confusing. You're going to watch this a few times, especially if you're one of my students, because they do struggle with this. It is, you know, it's confusing. I keep reiterating, it's just Ohm's law, it's just Ohm's law. And it's really easy once you kind of get that, but it does take a while to trust that fact. So anyway, we can calculate our capacitor now. 1 over 2 times pi times the frequency, which in this country is 50 Hertz, times the value we got for our inductive reactance, which in this case we're using as XC, so we can calculate the exact capacitor we will need to create unity, 450.98. So it's telling me I need a capacitor that big. So we got 7 microfarads there, or 7 times 10 to the minus 6. And that's the size of the capacitor I would need. So if I just redraw that circuit, you know, very quickly, the tube goes there, and then that comes in there, and our ballast went there. The capacitor, I'm going to put it in parallel. So I need a 7 microfarad capacitor. That's all of that was just for that. But there you go, that's how you calculate it.
So there you go, that's how you calculate that stuff. Hope it helps with your science module, and I'll see you next time. Cheers.